Hello, everyone. Uh, Welcome to the ECE webinar series for the summer semester. This is the first seminar in this semester. And it is my distinct pleasure to welcome today's speaker. Professor Biswajit Ray is an assistant professor of ECE at the University of Alabama. There he directs hardware reliability lab, and he has received a PhD from our school, in fact, advised by Professor Alam. And after he graduated from Purdue, he worked in SanDisk Corporation, where he developed 3D NAND flash memory technologies. Dr. Ray holds 15 US patents and has published more than 50 research papers. He's a senior member of IEEE and has received the Outstanding Faculty Research Award from the University of Alabama. And today he will be talking to us about his research on 3D NAND-based storage systems for hardware security, reliability, and edge computing. So please join me in welcoming Professor Biswajit Ray.
Thanks, Dr. Gupta, for introducing me, and thank you for this invite. And thank you everyone for coming and joining me for this talk. And so in this talk, my goal will be to introduce the 3D NAND, the technology aspects, and my research, my experimental research, how I conduct on experimental way or on the 3D NAND chips, commercial off-the-shelf 3D NAND chips, for addressing the challenges in hardware security, radiation reliability, and edge computing. So I have around 30 slides, and I plan to complete it in 45 minutes so that we can have some more discussion after the talk. Okay. And you can ask me question in between anytime you like. So you can just put in the chat box. Maybe Sumit can interrupt me. I will be happy to answer them during the talk as well. So here is my background. So I did PhD from Purdue in 2013, and then I joined SanDisk, which is now part of Western Digital, as a device engineer there, and we developed, means I was part of the team which developed 3D NAND. And then from 2017 onwards, I am an assistant professor in the University of Alabama, Huntsville. My group currently has 6 PhD students. 2 of them, Sakib and Preeti, very recently graduated with PhD, and one joined in Intel, another in Micron. And we all, all the students work some part of this is flash memory or solid state storage to some of this problem as I've depicted here, either in hardware security or say radiation environment, edge storage, or neurocomputing using solid state storage as the media. So many of the concepts that we are developing, we are testing them on 3D NAND or NAND storage, but some of these concepts are quite generic and can be also transported to other technologies as well. Okay, so I'll talk about some of those research as I go forward. So that's just to show you my current research interest. So our work is currently funded by mostly NSF. So we have currently 3 NSF awards going on, and the radiation efforts is mostly funded by DOE. And we also have some DARPA funding on some of the research activities we have. And I have established collaboration with Sandia Lab mainly for radiation sources, because to do in the radiation source are very rare, looks like in the university environment, but Sandia Lab has very good calibrated sources. So we go there to perform radiation experiments. I still have collaboration going on with my previous employer, SanDisk. So they send us chips many times. So we work on SanDisk also closely. And Vanderbilt University is very close by, so we also have collaboration there. Okay, so that's the motivation for my talks, that we are right now in the zettabytes era. So we heard about megabytes, we heard about gigabyte, but zettabytes is a new units. I mean, you can see. So it is in terms of bytes, it is 10 to the power 21, or in other words, it is 1 trillion gigabytes, right? So for example, one thumb drive we buy is in around 32 gigabyte. So it is 1 trillion gigabyte. This is the data globally we generate every year. And it is projected. So this chart is from IDC, which is International Data Corporation. That's the global data sphere. They're defining global data sphere as the all digital content created in a year. So that is going to exceed, say, 175 zettabytes. So that's a huge number, right? So, and one of the main primary contributor for this increased data is these edge devices or Internet of Things applications. Okay, yeah. So, yes, I think if you have questions, you can always ask me. Otherwise, I think you should please mute, as Sumit is saying. Okay, so I think so that's the motivation, that the amount of data that is growing every year is huge, humongous, and bit density of this storage is a challenging thing. But it is not just the bit density. If you look at where this data is created, it's mostly at the edge. And if you look at the edge devices, there are other challenges as well. Some of them related to security, data security or hardware security. Some of them related to energy efficiency, because most of these edge devices are run by, say, limited power sources like batteries. So we need to store, we need to compute with energy efficient way. Privacy is another important consideration, because whatever these edge devices, even though they are low cost, but they are generating high value of data, and that needs to be protected, and the privacy has to be protected. So this data privacy is another challenge. So all these challenges are cannot be solved just by single device design. We have to have innovation coming up from the system design as well. So, and more specifically, I would like to say more interaction between device and system, because what happened over the last few years, that system design has become more like technology agnostic, because that's how it will be very quickly adopted for any technology, right? If it is technology agnostic. But by making the system design technology agnostic, it has created few problems, because we are not utilizing the rich properties of the underlying media. So that is where my research comes in. So I like to introduce a lot of functionality in the system that are based on intimate interaction with the device. So in this talk, I'll talk about how system and device can be made interactive during the runtime of a product. Okay, so that's the motivation. And let's see. So in terms of storage technologies, there are many in terms of, say, need. So there are certain storage which are archival. Archival means we just store for long duration. We don't access them quite often. So tapes are one of them that is used. Sometimes hard disks are also used for that. So this is the storage hierarchy. It's not the storage hierarchy. So at the bottom it is the archival storage, and then in the middle we say this normal storage, which is predominantly still governed by hard disk in the data centers and all. But in the top in this hierarchy is this premium storage, which is, say, fast access. So flash offers that, and this flash media is becoming ubiquitous. If you see the consumer electronics space, hardly we buy these days laptop using hard disk, right? We buy laptops using SSD. And all other products you can see SD cards, starting from smartphone. And even in space application, flash is so attractive because of its lightweight. Hard disks are heavy, so in any space vehicle they want lightweight things. So one is lightweight, another is the high density. So there is no other technology that can give you more than 10 gigabyte per millimeter square space, area. So that's the highest density flash offers. So that's why it is attractive, and there is a lot of promise still going on, that this bit density is going to increase by orders of magnitude in the coming years, because of this innovation in 3D NAND. So that's the landscape, the storage landscape. And in this talk, I'll focus mainly the flash technology and what is going on in the industry, and how we can utilize this technology for creating different functions like the hardware security, edge computing, or other reliability enhancing functions. Okay. So this is the outline for my talk. So in the first part of my talk, I'll discuss the overview of NAND technology, the scaling trend, the device physics, and the system view, that how NAND storage solution work, what are the system architecture we need to make it work. Then I'll talk about my research on hardware security using this flash system. So how to make the storage solution more secure, right? So this physical unclonable function or PUF, true random number generators, TRNG, watermark, flash DNA. These are very brand new security primitives. So I'll introduce them using the device properties of flash memories. Then I'll talk about edge computing or edge storage. What are the challenges? How to make sure that privacy, the data owner or that the data users' privacy is ensured. How to use computing using this 3D NAND. And finally, I'll talk about radiation effects that for space storage, right? How or why this flash memory is vulnerable to radiation, and how to come up with system solution to make this entire system radiation hard. Because this is an interesting area, because for NASA or other space agencies, they cannot fabricate, for example, a custom designed flash memory solution for their needs, because the big companies like say Intel, Micron, they don't have any separate product line for radiation hard design. So all they do, they buy these commercial off-the-shelf chips, and they make their own system so that those chips can tolerate the radiation doses in the space. So that's where a lot of challenges are, a lot of interesting research going on. So I'll talk about that in the radiation effects discussion. Okay, so that's the overview, and I'll start talking about one by one. So I have around 30 slides, so I think should be done in 30-40 minutes. So this is the technology evolution of this NAND industry. So there are not many companies who makes or fabricate these NAND chips. So you can see this SanDisk Toshiba, they have a joint venture. So this is one, Intel, Micron, SK Hynix, Samsung. These are the main companies that make these NAND chips. So one is NAND chips, another is the NAND solution. Solution is like the thumb drive. So thumb drive comes with NAND chip as well as a controller, and I'll talk about it in a couple of minutes. This controller makes many companies make these controllers, but these chips are made by very few companies. So around 2015, so you can see there is a transition happening. So this is the transition, very important transition happened in this NAND industry. This is called 2D NAND to 3D NAND. So till 2015, most of these companies were making only 2D NANDs. That means it is like on a single wafer, every cells are sitting on a plane. But from 2015 onwards, the NAND industry has moved towards 3D NAND direction. And currently, I think all the chips that is generated or produced by these companies are all 3D NAND. So I mean, uh, just to give you a perspective, so by making 3D, so you are increasing the bit density per unit area, because this is the metric. This is the most important metric, that what is the storage density, right, for storage industry. So we say 10 gigabytes per millimeter square. So if we stack more and more bits in a third dimension, you can increase the bit density. That is the motivation, and that will reduce the cost as well. But 3D is a difficult technology, but it is successful now, and there are a lot of challenges, and I'll talk about them. And 3D is still at its early stage. That's what I would like to say. So right now, if you see, I think last month I saw 176 layers. So layers is the number of, say, stories. It's like a multi-storied building. So more layers, you have more density. So currently, Micron is producing in this 176 layer, and it is projected that by 2030, it will be having, say, 1,000 layers of 3D NAND cells. So that is the projection from the industry, and I think very quickly, industry will move towards the direction. So the bottom line here, I would like to say that 3D is still in its early stage, and there are a lot of challenges needs to be overcome as 3D goes in this 1,000 layer direction. Okay, so this is the new scaling direction for NAND industry, the number of layers. Earlier days in 2D era, we used to say, what is the size? Like 20 nanometer, or it is 34 nanometer, or 16 nanometer. This is how we used to define technology node. But now in 3D, we always say, is it 32 layer, or is it 64 layer, or is it 128 layer? So that's how the technology is moving now in the 3D NAND era. just to give you a architectural perspective that how 2D looks like as a array point of view. So this red lines you are seeing, these are the bit lines, and this green lines you are seeing, these are the word lines. So any memory has bit line and word line and then substrate. Now in 2D, all your memory cells are sitting on the substrate. This blue bar you can see here is the substrate silicon wafer. So so these 2D cells are good because they are made on silicon, crystalline silicon wafer. But if you see 3D, this is like a pancake structure. So you have these green plates, these are word lines. So these individual word lines, and there's a vertical pillars. If you see closely, there's a yellow vertical pillars running from bit line to the ground. So these vertical pillars are made of polysilicon, because this cannot be, these are grown, this silicon is grown. And I'll talk about a little bit how they are grown, but the main point here is this cannot be crystalline silicon. The crystalline silicon is the wafer sitting at the bottom, the substrate. But the channel material where the transistor, individual cells will reside, they are basically made of polysilicon. And it has introduced a lot of challenges as well. But this is the architecture in 3D. So so it requires a lot of deposition and some of the techniques that I'll come to this in a couple of slides. But just to give you an idea how this 2D NAND looks like and 3D NAND looks like. Okay, at any point if you have questions, let me know. So that's just to give you architecture of array. But in terms of cell, so just you want to compare one cell of 2D versus 3D, you will see, yeah, so I think before I come to the cell, so let me give you the fabrication idea, right? That's what I was saying, that how this is why it is polysilicon, why it cannot be crystalline silicon. So this is the reason. So the way 3D is fabricated is we deposit different alternative layers of the poly and oxide as a pancake structures. And then the most important step in this fabrication is this etching process. That we have to drill hole or punch hole up through all these layers. These layers are the number of layers we are saying, right? 32 layers or 64 layers 3D NAND. So each this poly layer will be acted or will act as a word line here. So now we have to drill a hole all the way from top to bottom, and this process is called reactive ion etching. So this reactive ion will come from the top, will etch out, and it will go all the way to the bottom. But now this is a huge aspect ratio. You can see the diameter of this hole will be in the order of say few nanometers, say 100 nanometer, the diameter of the hole, and the length will be in the, or the height of this hole will be in the micrometer range. So now this reactive ion etching will not be as efficient as it is in the top versus as efficient it will in the bottom. So now you can see there will be a lot of layer to layer variations, because this etching process will be more efficient in the top layers. But as you go down to the bottom, there will be a lot of inefficiencies in the etching. So, and this is going to continue, because as the number of layers are going to increase, this aspect ratio will become more and more steep. And that will introduce another variability or another challenge for 3D NAND, which was not there in 2D, because 2D everything was on a planar. So there is not much variability issues from one say one word line to another word line. But here every layer is separate word line. So there is word line to word line variation is huge. And if you can do, I mean, you can do some back of the envelope calculations. Typically this tapering angle is in the order of half a degree. So if you assume this half a degree, you can find out from the height that what will be the diameter difference, and it is in the order of 45 nanometer, and the entire diameter is around 90. So you can see almost 100% variation. You can see means it will be almost double diameter in the top and diameter in the bottom. They will be almost 2 times. So this is another challenge, and that may restrict the number of layers you can grow over the time. Okay, so now let's come to cell structures, the how 3D cell and 2D cell looks like. And that's where I think I would like to introduce the basic device physics as well, that how a flash memory cell stores information. So flash stores information in the form of charge, because charge-based memory. So there's a floating gate. So this is nothing but a MOSFET transistor where there's an extra floating gate in the gate stack. So you store electrons, we say the cell is programmed. And if there is no electrons on the floating gate, we say the cell is erased, or it represents logic 1. So for example, when you buy a brand new thumb drive, say from Amazon, all the bits will be one. I mean, all the memory cells will be one because none of the cell is programmed. So all the cells are in the erase state. The moment you write some movie or some file in that thumb drive or in that SSD, you are selectively programming certain cells, and that's how you are creating or storing information 0 and 1. So the bottom line here is the flash is a charge-based analog memory, and we store information in the form of a charge on the floating gate. Now, in terms of architecture, the 3D NAND, in terms of device physics, it is same. It is also a floating gate memory, but in terms of cell architecture, it is very different because you can see 2D was fabricated on a crystalline wafer, so it is a two-dimensional MOSFET. But 3D is grown. So this you make the whole memory hole, and then you deposit polycrystalline silicon in that hole, and that's how your gate stack is developed. So 3D is a gate all-around transistor, and the channel material is polysilicon, or has to be polysilicon, because you cannot grow crystalline silicon in that fabrication steps. So these are the differences between 2D and 3D. So one is crystalline silicon, another is polysilicon. One is the planar gate. We used to say 10 nanometer technology, 20 nanometer technology, like that. And in 3D, it is the now number of layers, and the gate length is still high these days. It is around 50 nanometers. So it is not as scaled. For 2D, the latest technology will be, say, 14 nanometer. But in 3D, all of the companies are making right now in the order of, say, 50 nanometer of gate length. So over the time, as the number of layers increases, I think the industry will shrink even 3D gate lengths as well. But currently, um, the gate lengths are quite high. The other important distinction is, you can see the doping. The 2D, you have source and drain. These are highly doped things. But in 3D, the source and drain are undoped material, right? Because these are continuous polysilicon layer. So all these things makes a lot of difference between 2D to 3D, and industry has to overcome a lot of challenges to make 3D NAND technology work. Okay. Now this is the system view, that how as a NAND storage solution. We talked about
So,
NAND
Mr.
cell.
Jeet, may I
Yes,
ask a quick question?
yes, please.
So if you go to the previous slide,
Yes.
um, so you mentioned that the source and the drain are undoped, right? So is this when the current is flowing, is this flowing through the whole polysilicon channel, right?
Yes.
Whenever the current is flowing, whenever these things are on, right?
Correct.
So how much typically how much resistance do we see in that path?
That's a very important question you asked, because this is the real bottleneck. So the source and drain, since they're undoped, their resistivity will be high. So now you have to rely on fringing field. Fringing field means so this control gate that also will have some fringing field, and then there is another control gate on top, another control gate on the bottom, because this is a series connected, like NAND chain. So now you have to rely on the fringing field to invert, and because of this reason, this on current is very low. I mean, 5, or I think an order of magnitude lower is the on current in 3D compared to 2D, because of this interlayer resistance. So, and that is going to increase, because the more number of layers you stack, you will have more and more series resistance together, and that will cause, I think, very low on current. So this is one of the challenge, and industry, I mean, trying different things to solve it.
Okay, thank you, Mr.
Yeah. Okay. Thanks. Okay. So yeah, this is the system view. So if you open up anytime your thumb drive or your SSD, you'll see there are two components. One is this memory chips, which are this rectangular shape, and there is a memory controller, right? So the controller actually is the brain of the system. Now, the controller does a lot of functions. For example, it performs error corrections. So why you don't see any memory errors when you read your, say, image or file? Because there is errors happening in the memory chips all the time, but you don't see as a user, because the controller performs error correction. It performs other, like wire leveling and other address mapping functions as well. So my research, my goal in the university is how to improve the functionalities of this flash translation layer, which is nothing but the controller. Okay, so this is the memory chips and this is the controller. So how to make this interaction more intimate between the memory controller and the memory chips, so that the memory system becomes more resilient and more efficient. So that's where my research goes. And if you look at how the memory controller interacts with the chip, so this is a good diagram, I'll say, that how you read, for example. So you have certain bits that are programmed. That means they have electrons on the floating gate. And the moment there will be electrons on the floating gate, its threshold voltage will be higher, right? So this plot below is shows or showing the analog threshold voltage distribution. Now, why I'm saying distribution? Because we are talking about millions of memory cells, right? Certain cells will be programmed, certain cells will be erased. So even though all the cells are erased, they will not have the same threshold voltage, because these are analog memory. Because of process variation, because of uh, the differences in the charge stored, there will be a distribution of threshold voltage. So that's why we are representing it as a distribution. Now, when you read that which cell is programmed, which cell is erased, all we apply is a reference voltage. We apply a reference voltage which lies in between of the erased state distribution and programmed state threshold voltage distribution. And that's how we find out which cell is erased and which cell is programmed. Okay, just by applying a reference voltage and see which cell is conducting, which cell is not conducting based on their threshold voltage. So this is one way system interacts with the memory chips and find out the information stored. But there can be a lot can be done, and that's what I will show in the next slide, that how system can make this more analog information out of the memory chips. Okay. Okay, so this is the experimental setup I use in my lab or my group use. So we buy those off-the-shelf memory chips, and this we plug it into a socket, and we have an interfacing device so that we can connect those pins of these memory chips, and we can interact with the computer interface. So that's the experimental setup. Now, what is the interesting part here is that we define the controller now. So since controller hides all those errors, information, or analog properties, so we don't see as a user the memory bits property. But if you really interrogate, or if you really want to use the analog properties, we have to design our own controller. So yes, so this is the framework we use for getting the device system interactive framework, right? So we send commands to the chips, and chips respond with the digital data. So this is at the end a digital measurement system for analog properties. And this is where I would like to illustrate how we conduct it. So this is a reference voltage, right? Reference voltage is used to identify erase state versus program state, or logic 0 versus logic 1. But we can shift actually this reference voltage. So if we shift this reference voltage, we will read another set of data from the same memory bits. And by doing so, we can reconstruct the threshold voltage distribution, or we can find out which cell is exactly what threshold voltage in terms of analog values, right? Because we can shift the reference voltage in, say, few millivolt range, say 7.5 millivolt range, right? We can shift it, read it, shift it, read it, and that's how we can reconstruct these analog properties or analog distribution. Now, what it allows us, it allows us to capture the process variation staying in the system side, right? We are talking about all system commands. We are not using any manufacturer privileged commands, right? We are using standard system commands, and still we can get back the analog properties of the underlying cell. The other method is we can say start performing any operation. Say, so you start erasing. So when you start erasing, your entire program distribution moves towards the left, but you can stop erasing at any point of time, right? So by doing so, you can put the memory state in an unreliable state. Unreliable means undetermined state, right? So certain cells will be read as 0, certain cells will be read as 1. And by doing so, you can again get the analog properties, distribution and all. So that this is the methodology we use to get the analog cell properties using standard system commands. Okay, so that's pretty much our experimental method, the way we conduct research on commercial off-the-shelf chips. So that's ends the first part of my talk. Am I going a little slow? Looks like so. Yeah, I think Uh, I have around,
Absolutely, you're fine. Yeah,
okay.
please.
I still have around 15 more slides. So I will little bit quickly will go now on some of this research that our group has done. And most of these topics are published already. So if you are interested, I can forward the corresponding papers, or you can look into those papers. So I'll just we'll shift the gear a little bit now on as I going through this research outcomes. So hardware security, right? So that's a very important problem, at least for NAND industry. It is important for any electronics, but for NAND industry, it is also very important because, as you can see, this is a horizontal supply chain, right? So here, there are certain manufacturers like say Micron, Toshiba, they make these chips. There are several distributors like DigiKey, Amazon. There are so many distributors through which you can get those chips. So many times the manufacturer directly does not distribute, because the manufacturer produce millions of chips, right? So, and you many times, or as a system integrator, you need to buy 100 chips or 1,000 chips. So you generally go to a distributor to buy it. And then the system integrator makes the entire system. For example, the KingFast makes SSDs, right? Marvell, they makes their own controller. So the system integrator many times becomes a victim because of untrusted distributor or untrusted the foundry employees. What do you mean by untrusted? So for example, distributor, instead of buying a genuine chip, they can fake the chip, right? They can just label it in a different name, or they can recycle some of the parts, because these days we throw our electronics components after 1 or 2 years of operation. For example, your smartphone, right? You use 2 years, you buy a new one. What happens to the components inside? They're still alive. This memory chips still remains alive. And this is one example. You can see um, how a, a counterfeiter or a untrusted rogue employees, they can pull out those chips and they can sell it as a brand new, right? As a system integrator, or many times as a customer, we don't really know whether those chips are genuine, are they brand new, or are they recycled, or are they remarked. So these are various issues happening because of this complex supply chain of this semiconductor industry. And this is a globalized industry, right? Many of the distributors will be different countries, many of the foundries will be different countries. So at the end, your system integrators becomes a victim, because they are unknowingly say, selling counterfeit parts, or customers are definitely lastly the victim. Just imagine in a say defense system or in an aerospace system, you are using a counterfeit memory. So counterfeit memory will have inferior quality, will have less lifetime. So that may lead to catastrophic failures as well in a critical application. So that's a counterfeit, or is a growing concern. And for NAND flash industry, it is more because NAND is ubiquitous, right? It is used in many applications. Okay, so that's the global challenge. Now, how to solve the NAND specific hardware security issues. So that is where my research comes in. So there are many primitives that can be used, like say PUF as a digital signature, or just like fingerprint, electronics fingerprint, right? Chip fingerprint. So what PUF does, it exploits this process variation, because every chip will have different process variation signature, and that is unclonable. So that's how I started research by generating say flash memory based PUF. There are many PUF construct. You can see SRAM based PUFs or ring oscillator based PUF. So there are many PUF constructs are there. So my contribution in this field is we generated this flash memory based PUF, and there are unique advantages of using flash memory based PUF. One is it is we don't need any custom design hardware for generating PUF. It's just on a commercial chips you can generate the PUF, right? We don't need any custom built circuit, and the number of bits are humongous, right? Flash is gigabytes of memory, so we can get a very long bit length of PUF. And how we generate it is pretty simple. We start with say all one or erase memory state. We don't fully program, we just use a partial program. So by partial program, you program certain bits, you don't program certain bits, and the bits which has say high threshold voltage due to manufacturing variation, they will be programmed fast, and the bits which have low threshold voltage, they will remain at erased condition. And that's how you get this random image or random signature. And this is an unclonable signature, and every chip will have different signature, right? This random image will be different. But for the same chip, if you use the same location, memory address, you will get the exactly the same signature. So this work you can see is published in TED, and once you get this, yeah, I think here I just want to explain a little bit more. So you start with the erase state, you start doing partial program, and you end up with a disturbed state. And when you read this disturbed state, you can find out which cells are highest BT and which cells are low BT. So here, right, we cannot probe individual cells because we are working on a commercial chips. So that's why we have to come up with these intelligent techniques that how to manifest all those underlying process variations. So this is the techniques we use, partial programs, and many others can be used as well. And at the end, we also can generate TRNG or random number generators by reading this memory state again and again. So once it is disturbed, the certain cells which are very close to the reference voltage, they will sometimes read as 0, sometimes read as 1. So this is exactly what I do. We read it multiple times, same memory address, same memory location. Certain bits will find they're toggling their states. And this is due to the read noise. And using this, we can generate random number. So that's one thing which published in TD again. So if you're interested, you can look into those papers, or I can send you them. So that's one thing. So PUF and TRNGs, I saw there was a lot of work on other electronics memories or platform as well. But as a group, this is one thing we came up as a brand new, which is called flash watermark. Now, this is a very important concept. If you think about how, how to solve counterfeit issues, right? So if, say, manufacturer can watermark some things on the memory chip that cannot be erased, that cannot be changed by anyone, right? Then it can solve many of these counterfeit issues. For example, say manufacturer writes its name or the date of manufacturing, right? So as a watermark inside the memory bits itself, inside the hardware itself, then even if the counterfeiter tries to recycle it, the system integrator will immediately know that no, this is not from, say, SanDisk, this is not from Toshiba, this is from some other companies. So this is one thing we developed as a group. So how you did it is a interesting technique called program and erase, right? So this is called cumulative defect. So when the memory cells comes out fresh from the foundry, they're all in a good state. We say so good and bad are relative war, right? Good, both are operating memory cells, but one cell is good condition, another cell is little bad condition, and we can selectively make certain bits bad. So this is the technique we used. So suppose we want to watermark, say, 2019. So we take this digital equivalent and we write the data, we erase the data, write the data, erase the data a couple of times, 1,000 times. And by doing so, we selectively make certain bits bad. So the bits which are changing their state, right, 1010, they will become bad, because these other bits which are remaining in the same logic state, so that means there's nothing happening in those bits, they will remain in the good condition. And this is the way we can make watermark in that memory chips, so that because nobody can make a bad cell good, right? So this is the logic we use to make sure that the watermark remains intact. And so this is a new encoding technique, I'll say. This is a new data encoding technique, which is not charge based, because charge based content you can erase, you can change, but this is a analog property based encoding technique. And we have demonstrated it on flash. It can do it on other memory technologies as well. So this work is published, I think, in 2 locations. Okay, so this is just to demonstrate. So yeah, so this work is published in IEEE TED as well as Design Automation Conference. We did it on NOR Flash, we did it in NAND Flash, and we published it. So if you're interested, you can see them. But this is the watermark imprinting technique, that this is how we imprint the watermark. Now, using system commands, how we'll retrieve, how you'll know that this cell is bad, this cell is good. So this is where this watermark retrieval comes in. So we start with all 0 data or black image, and then we will apply a partial erase operation that will not fully erase, right? All 0 fully erase become all 1. But if you don't fully erase, we'll see the watermark data. So here we watermark with the Einstein image inside the memory. And you can see the image is gradually becoming visible as we do partial erase, right? So this is very similar, like, say, the steganography, right? The way we used to work earlier days with some onion ink, that on a blank paper, you see a white image, but the moment you put the image under, say, heat, or under candle, you'll see uh, the hidden contents is coming out. So this watermark can have multiple application, not just say saving manufacturing data. It can be used even for steganographic application as well. And this is the more evaluation results. We did a lot of detailed analysis on this, and you can see our DAC paper or TD paper just last year they got published. Okay, so that's the watermark thing, and I'll go to the next innovative uh, hardware security parameter called flash DNA. So this is to identify that which manufacturer, right? So or which foundry this chip is coming from. So every foundry has its unique equipment, and based on that, there is a unique signature in the memory. So in a logical way, when you analyze memory bits, you see everything is ones or zero. You don't get to know the underlying manufacturing process difficulties, right? So here, what we used, in a flash memory block, when you erase, we erase flash memory in a block by block. But in a block, there are multiple word lines. So we found that certain word lines are slow to erase, certain word lines are fast to erase. So this is a unique pattern, and every company has different pattern. For example, here is the evaluation results. So here x-axis is the page number or word line number, and y-axis is the erase efficiency. That means one word line is slow to erase, one word line is fast to erase. So we see unique pattern between the word lines, and this pattern is same for all the chips coming out from the same foundry. But if you change the manufacturer or the foundry, we see a different unique pattern. So that's this pattern is very, I mean, we gave the name DNA because we can identify a family of chips coming out from the same foundry. Okay, so this DNA is nothing but a signature for a family, unique family. If you change the family, even in a Toshiba, right? Toshiba can have multiple foundries, multiple fab location. Based on that, this signature will change. Okay, so this work has been published in TD, and this is not yet online. It will come online very soon, but I can give you preprint if anyone is interested in this work. So that ends my half of the talk. I'm still having 10 more slides. It should be done in 10 more minutes. So hardware security, now this edge computing and edge storage, right? That's another hot area of research in terms of energy efficiency, in terms of privacy, how to preserve privacy in the edge. Well, these are the challenges of any edge computing or storage platform, right? So it has to ensure privacy because these edge devices are operating in unmanned areas, that data can be hacked, data can be stolen. So how to ensure the data is sanitized? When you delete something, it is completely deleted. This is another issue with flash, that it remembers. Even if you delete the data, people can gather, or hacker can retrieve those data. So that's a huge privacy issue. Energy efficiency is another important issue. They're run by batteries and all. Low cost, resilience, edge devices in harsh environment. So this is another lot of challenges in the edge storage. This is where one of my research goes on, that how to make this interactive framework so that we can ensure or you can address some of those challenges. So I because of time, I will just focus one or two problems that we solved here. So one is this sanitization issue, that how to ensure privacy so that so suppose you have created certain images, or you have taken photos through your smartphone and stored them, and suppose you want to delete one photo. So the moment you delete, actually it is not deleted fully, because in the media, in the storage media, those photos is still there. You are just changing their address or making those address invalid, but data is still there in the media. So if you lose your thumb drive, somebody can get all your personal information, or all your data that is deleted already by you from the storage media. So this is one sanitization commonly used, and you can see it is not secure, this logical sanitization. There is encryption based sanitization, but this also has some pros and cons, that how we'll manage encryption key, and this also becomes your storage system more costlier because you need to have encryption engine. The most commonly used sanitization technique is called override based sanitization, that you, instead of making your entire memory block being deleted, you make one entire page to be all zero, or you override the data, because if everything is zero, you say that page is deleted, right? So this is one um, digital way of sanitization, that by overwriting the content, you make everything to be in the same logical state, and you say that data is deleted. So this is the most secure and the state of the art sanitization method. But what our research questioned that this is also not secure. This override based data sanitization is not secure. One can get the data back even if you make everything zero. Some smart hacker can get the data back. So this is why we published one paper in Unix security. So, and this is the premises that this is how you store the data, right? Zeros and ones. And then after few years or after few days, when you delete the data, then your zeros, the program state will drift down because there is always a data retention or charge leakage issue. That is analog memory, right? Analog memory, that means even though digitally they are zero, but in terms of threshold voltage, analog threshold voltage, it will be little drifted down. And then when you create all zero, right, when you overwrite, then you are creating new set of zero, which will be strong zero. That means their threshold voltage will be higher. Yes, logically, everything is zero, right? Because everything is above VRAM, but physically they are not identical, right? So this is where we attacked this system, and we demonstrated that even after all zero erase, you can get back the data. So this is what we did. We again wrote the Einstein image. So this is the digital representation, and the analog threshold voltage is shown below. Then we, instead of waiting years, we just baked it because that accelerates the data retention. And by making that, we are ensuring that the cell is drifted down threshold voltage. And then we perform this all zero scrubbing. So now your image is deleted. When you read logically, you don't see Einstein image. But then we did a partial erase operation on this image, and we see the Einstein image back. Okay, so that's a huge attack. I mean, that's a huge theft. I mean, vulnerability in the storage system using NAND, because you can recover the data even after state-of-the-art erase technique. So this work has been published in Unix security. I think it is the paper is there in my webpage. You can see that if you're interested. And finally, we also did some work on computing aspects on using NAND, 3D NAND architecture. Or so here I mean, in this paper, IEEE TDMR, we just showed that how NAND flash can be used as a weight storage device. So most of the time, you don't do training on the edge devices, right? We do training in the data centers, and then we store those weights only for inference in the edge devices. Now, how to store those weights so that even if some errors happens in the memory, still you don't incur much accuracy loss. So that is the question we asked. And in this paper, we demonstrated how we should store the trained weights on the edge computing platform so that we don't incur much accuracy loss. We are also using the architecture itself for computing purpose, but in this work, what we did is just as a weight storage device, right? So we stored those trained weights as an 8-bit digital representation in 8 bits way, and then we performed reliability experiments. Some of those weights got changed, and then we reconstructed those weights based on these bits and computed the accuracy, and we saw the accuracy will lose over time because of data retention and other issues of flash. Okay, so that brings to my last part of the talk, and I think I should be able to done in next 5-10 minutes. Okay, so then we'll have more question after that. So we talked about security, we talked about computing. Now let's talk about reliability in the extreme environment. An extreme environment, specifically like radiation prone environment for space or defense application. Okay. So these commercial flash memories, these are not designed for extreme environment. These are designed for terrestrial normal user application. So radiation tolerance is not a concern. I mean, when I was in the industry, we never did any radiation reliability testing because it's not a concern. The usual radiation that you go through in an airport check or airport X-ray scanner, that will introduce error, but you have always error correction, right, in the system. So system will error correct all those errors. So that's why we don't care much on the radiation side. But in a prolonged radiation environment, right? Say in a nuclear power plant, for example, electronics, or say space. So you need to care about radiation, and NAND flash is very much vulnerable to ionizing radiation, preliminary because it is a charge-based memory. So whenever radiation comes in, it ionizes this oxide, and oxide ionizing will create electron and hole pair. Right, so this is the energy band diagram. If you look at, this is a program state energy band diagram. Everything is grounded. So it is a normal your flash memory just sitting idle there. Now whenever radiation comes in, because there is electric field in the oxide, right? So electron will move out after ionization, but hole will remain in the oxide, or it will go in the floating gate and will recombine with the electron. So that's how the more you are exposing to your chips to the radiation, the more you're losing charge, right? Because every time a radiation goes through it, say radiation particle or say ionizing gamma ray goes through it, you are creating electron, and whole electron moves out, but hole remains in the system, either trapped in the oxide, or it goes to the floating gate and kill one electron. In either way, you are losing charge. So what we demonstrated that why this problem is severe, because there is a lot of technological innovation took place, right? From say 100 nanometer technology node to 16 nanometer technology node, from 2D to 3D. No matter what, everywhere we found all these technologies found to be very much vulnerable to ionizing radiation. And reason is you can explain using this um, simple equation. So how this flash memory you can think about as a capacitor, right? So this is the charge storage node. So delta q and capacitance is this ono stack capacitance and change in threshold voltage, right? This is the starting point, how to understand the radiation effects, that threshold voltage will drift down as it is exposed to more and more radiation, right? You'll lose charge. Now how much charge you'll lose, that depends on how many radiating particle, what is the area. So interesting thing is area cancels out, because capacitance is also proportional to area, and the amount of incoming radiation particle, right, or the radiation photons, this is also proportional to area, right? So area dependency goes out, and at the end you come up with this simple equation, the Tox square, the oxide thickness square, right? This is the oxide thickness, and oxide thickness and ono thickness has certain ratio, fixed ratio. So that's why this equation can be simplified in this form, that oxide thickness square. That means if you don't scale this oxide thickness, even if you make a small device or big device, your threshold voltage shift will be same and your tolerance will not improve. And oxide thickness did not scale for flash memory preliminary because of, or primarily due to data retention constraint, right? We have to ensure that data is retained for 10 years. So that's why oxide thickness is always remained in the order of 8 nanometer to 10 nanometer range. Unlike logic devices, in a logic devices we have scaled oxide thickness, so 1 nanometer to up to 1 nanometer, but in flash memory we cannot do that. And since oxide thickness did not scale, the radiation tolerance also did not change much. So that is the key physics, device physics of how radiation interacts with the flash memory, and and why it is still remain vulnerable, no matter it is 2D NAND or 3D NAND or ultra scale devices or less scale devices. Okay, so now my group mainly performs system approach, that we will identify these errors in the memory chips, we'll identify the pattern, and then we come up with system approach, because we cannot change the device. This is a fundamental physics that it will be vulnerable. But coming up with some system function, we can actually you can extend the lifetime of these devices, or tolerance limit, radiation tolerance limits of these devices. So we have published several papers. This is one of them, you can see, and we have demonstrated with real experiments under radiation environment that if you use some of the system commands or system algorithm, we can really improve the radiation tolerance of this chip without changing any hardware. We are buying commercial off the shelf, but we can still extend the lifetime of this memory. So yeah, I think I have one more slide. So this is another exciting area of research we are doing, that we found that memory is vulnerable to radiation, but can we use it as a radiation detector or radiation sensor? Just think about, right? Every smartphone has SD card slot. SD card is nothing but a flash memory array. Now, you don't see errors in the SD card because you always error correct it by error correction code or using the system command. But you can bypass this error correction code, and you find out, you can collect exactly what is the number of bit flipped. So this is the concept you can use to make every smartphone as a radiation dosimeter, right? So you can, as a nurse, for example, they will know the every day how much radiation they are getting exposed, or as a air crew, they will know how much radiation they're getting exposed. So this is one idea. It's got funded from NSF, DOE, and we have done a lot of research on this. Papers also as their patents, the how to use this smartphone or how to use basically this flash memory as a radiation dosimeter. Yeah, so, and we are the one of the first group to show radiation effects on 3D NAND. So as I discussed in the beginning, that there are different layers in a 3D NAND architecture, and we found that different layer reacts differently under radiation. There's a lot of layer to layer variability, and we see a unique U-shaped pattern in when 3D NAND is exposed under radiation. Different layers are having different radiation concerns, so that can be used for making controller more intelligent and all. So I think I'll stop here, and if you, most of this work that I discussed today are online. You can find if you're interested, or you can ask me, you can email me. This is my email ID. You can email me. I'll be happy to give you the papers or more information on any of this topic. Thank you. Thank you for listening.
Thank you, Mr. Ji. Thank you so much for a very interesting and insightful presentation. Thank you. So the floor is now open to questions. I have one question in the chat, so maybe we can start with that. And as the audience is thinking about the questions, please feel free to unmute yourself and ask. Okay. So this is the question from Muhammad Abu Khatar. So he's asking, what aging phenomena causes a bit to be bad?
What aging phenomena
causes a bit to be bad?
Oh, yes. So you create defects in the oxide. So the more you say program and erase, you are moving back and forth electrons from the floating gate to the transistor channel and from the channel to the floating gate again. So as electrons move or tunnel back and forth between floating gate and the channel, it creates defects in the oxide, tunnel oxide. So that is the oxide defects we are talking about, bad cell or aging effect. So did I answer this question, or you have further on this? You can unmute and you can. Yeah, I can.
Yes, you did answer the question. Thank you very much.
Great. Any other questions for Professor Ray? I had a question.
Yes, please go ahead.
So some of the security aspects that you talked about, and as well as the reliability and the radiation related aspects, right? So how would the 2D versus the 3D array compare? Some of these are they similar, or are they different in these respects that you covered in your talk?
Yes, that's an interesting question, and we are trying to compare many times. I mean, because we have 2D chips, 3D chips, but it is not many times apple to apple comparison, because see 3D right now it is a big cell. It is channel length is in the order of 50 nanometer, and it is polysilicon. But overall response wise, 3D is still better now because it is bigger cell, reliability is better compared to ultra scale 2D. Ultra scale 2D is say 14 nanometer or 16 nanometer 2D cell. So in terms of reliability, 3D is better because it is higher geometries and all. But I think going forward, how it will happen, that will tell. I mean, time will tell. But I think other problem like say temperature issues are more in 3D because it is polysilicon channel. So polysilicon has lower current, as you mentioned, right? That is the interlayer region, and overall polysilicon has lower mobility. So from that point of view, noise issues are more on polysilicon. So from that point of view, 3D is bad compared to 2D. But doing an apple-to-apple comparison will take, say, you have to choose an older generation of 2D when you want to compare with 3D. But some of the security, so some of the security functionalities like PAF, TRNG, watermark, we have demonstrated both on 2D and 3D.
Okay. Thank you. That answers my question. Thank you. Any other questions? Okay, so there is one more question. When using the watermarking method, are there any disadvantages in terms of the space available to the consumer?
Not really. I mean, there is. I mean, this is a important question you raised, because when you have to reserve a block, for example, for watermarking. Now, a flash memory chips comes with thousands of blocks, minimum thousands, and there are a lot of extra blocks as well. They're reserved blocks. So a manufacturer can use one of these blocks just for watermarking, say manufacturing related information. That is, it is a valid chip. It is not a foundry rejected chip. This is the year it is produced. This is the company it is produced. So in that way, you just reserve one memory block, and that way that way it will not consume too much of space. But watermarking can also be used for hiding information as well. Steganographics, that is up to the system designer. The system can come up with some functions during the operation, during the memory operation, or on the field, they can perform this watermarking and hide information. So that is some different application for security. But in terms of solving and counterfeiting issue, I think it will not cause much of the space.
Thank you, Mr. Jeet. So maybe we have time for one more quick question. I think there are very interesting discussions going on, but we are unfortunately out of time. But maybe one more quick question, if anybody has. So feel free to unmute yourself and ask. Okay, if not, then let me thank Professor Ray for this wonderful talk, and thank you all for attending this talk. And have a nice day.
Yeah, and thank you everyone. And if you have questions, please feel free to email me. I'll be happy to answer even through my email. And thank you all, and have a good day. Yeah, thank you everyone. Yeah.
Bye-bye.
Bye.